The system control command is a primary way to interact with systemd. We'll use this tool to control basic service management as well as some more advanced capabilities that we'll look at later on. System control status is a great example of how systemd improves day-to-day administration. On this system, we can see that Apache has been configured to start on boot. It's been modified using a drop-in config file. It's up and running. We can also see the current bandwidth stats, primary and worker PIDs, and recent log messages all in one place. Modifying how systemd manages a service is simple. Viewing the current drop-in file tells us that systemd has been configured to automatically restart if the service fails, disable the killer, and the cgroup controllers for CPU, memory, and disk have been enabled. Next, let's watch the status of Apache to see how quickly systemd detects a failure and restarts the service. We can see the service has an uptime of about 4 minutes. Instantly, it's back online responding to requests. One of the more exciting capabilities of systemd is the out-of-the-box implementation of Linux control groups. In short, this allows control over the allocation of CPU, memory, and disk while system resources are under contention. The systemd cgls command shows the current cgroup hierarchy. By default, the system is split into a user and system slice, each having equal time on the scheduler. To demonstrate some basic tuning capabilities, I'm going to generate a CPU-intensive load to represent a user's application. The bottom left terminal is running systemd cgtop, which, as the name implies, gives us a top-like view of the cgroups to help us tune. The bottom right window is running top so you can compare the views. Notice the user slice has access to the entire CPU when nothing else is contending for it. Next, I'll start placing load on the 2 Apache services running under the system slice. We can see that each slice is using approximately 50% of the processor. Not only can we tune the amount of CPU at the slice level, but we can also tune services running within a slice. The CPU shares property defaults to 1024 and can be raised or lowered depending on the amount of CPU to add or remove. By default, everything is treated equally, and this works rather well for most workloads. Using system control, we can tune cgroups in real time. Lowering the CPU shares to 300 of the user slice restricts it to about 25% of the processor. Conversely, we can increase the CPU shares for the user slice and give our application closer to 70% of the processor. You can see that both Apache daemons are getting equal time inside the system slice. Let's lower the CPU shares to give our dev instance less CPU. Now, instead of each service getting 50 split, they're closer to 70-30%. Both of these examples illustrate how easy it is to restrict or prioritize applications based on the need. Thanks for watching, and I hope you enjoy systemd and Red Hat Enterprise Linux.